And I have one more task to do before I can relax and sit down. And this is to introduce our first speaker of a keynote. And I'm especially excited to welcome Thomas Zurbuchen here. I think it's not often that you have such a celebrity here in our Swiss Polar Day to speak to us. And how it is with celebrities, they're often claimed by many institutions, for example, the NASA, the ETH, where he's working now. But I'm very proud to introduce Thomas today because he started his career at the University of Bern before he went to the US. So after finishing his PhD, he went to the US, where after staying at the University of Michigan, he later became the NASA Director for Science Missions, and where he was leading a lot of those science missions in many years. He returned to the ETH only a couple years ago and has already left his mark. You may have seen this in the press, that he was able to really gain some significant funding, 100 million for a new research center, which is called GeoLab. And you can see he is unstoppable. And so I'm really glad that we have you here today as a speaker. I think the talk, which, it starts already here, the video, I don't want to do that. The title of the talk is The Edge of the World and Beyond, and I think it will tell us a little bit that there are parallels between Antarctic research and space research. And so I'm looking forward to your presentation, to maybe presentation about where no man has gone before. Thomas, the floor is yours.
Yeah, I'm so excited to be here with you. And before I start speaking, I want to just acknowledge that it's 5 years that Connie Steffen left us here on Earth. And I was lucky enough to get to know him before he passed. And I just want to encourage those of us, especially students who were not around when he was still active in the field, to go do research, because his career is truly inspiring to all of us, to have a career of purpose and a career of truly international reach, starting right here in Switzerland. So I want to acknowledge the amazing work and the inspiration he has been for all of us, including me. The story I want to talk to you about has two highlights. The first one is that I believe it's time to look for the polar regions. Yes, the way many of you are, as the Achilles heel of our climate system, and really figuring out how that works, but also as a proxy to really examine questions that we actually want to answer elsewhere, namely in ocean worlds around the giant planets in the solar system. I want to tell you how we think about that and what such an activity could be. The second thing I want to do is talk a little bit about GeoLab, which is right here in Switzerland. So unapologetically, we'll focus on Switzerland, not on Germany, not on Austria, not on fill in the blank, but Switzerland. Not because we don't understand the other things, but because like one of my good friends, a lead investor of some of the top companies, says before you can apply big ideas to the large masses, you need to think small and learn. As we look at the abundance of space data from Earth and the emergence of new tools such as AI and machine learning, we need places where we can look small and and I don't know a better world in terms of its instrumentation density, in terms of its technological abilities, but also in terms of its diversity of landscapes to make Switzerland the ground zero, if you want, of calibration of AI models that, of course, we want to scale and go to places like the Himalayas where similar problems arise, like the ones we're solving right now in Valais. So those are the two topics, outer ocean worlds and GeoLab, and of course they're overlapping in the middle in the polar regions. Does that make sense? That's what we're going to do in 40 minutes or so, and move on. So basically, when you think about polar worlds, you wouldn't necessarily think of this landscape. That, of course, is the landscape that I grew up with. You see a lot of stuff that relates to many of the questions that you look at, that you think about, including ice that's melting. It's very clear that the way the world looks from near Thunersee is different than it used to, visibly even far away, because some of the glaciers are no longer as magnificent and big as they used to be. The water that they're creating, not only in just melt, but also in of course, weather events like the ones today and others, are of course both a treasure, but are also a challenge. Sometimes down the hill are part of the energy source of this country. But for me, the thing you perhaps didn't look at is the sky. I think some of the coolest parts of that picture is the sky, because the sky is really dark. You don't see that because the picture was taken during the day. And for me, the reason I went into science, and you should know, I couldn't really decide what to do, whether astrophysics or earth science at the University of Bern. And thankfully, that school is so flexible, they'll let me do both. And at the end, I went the astrophysics way, but you should know I was really lucky to sit in classes with Erskine and all these people that of course I treasure and I never lost track of because of the work that is there. I did focus on the sky, and especially stories that relate to it, and this is one of those stories. And of course, it's a simple drawing. It's a drawing made by Galileo Galilei after he looked through a toy. Somebody sent him from Amsterdam. It's basically a tube with two lenses, glass that was shaped, not in a flat way like church windows, but in a shaped way that broke the light. And all of a sudden he looked at Jupiter, and what he saw is these celestial bodies, and it was clear that they're related to each other, and they broke every rule that there should have been that people talked about in schools, namely these celestial bodies indicated in stars were orbiting the other one, Jupiter, in a way they shouldn't, because as everybody knew at that time, the center of the universe is the Earth, and everybody should orbit the Earth. Of course, what happened, we've learned about these. By the way, it ended up badly for him. If you oppose the common wisdom of people, sometimes you take a little bit of a beating. Some of you have that experience from time to time. But what's really important as scientists is that we talk about science. We talk about it, and sometimes, when I look at this, history will give us right, and we better do that. What we have learned that these bodies, these celestial bodies, are much more interesting than we ever thought. Yes, there's Jupiter with its amazing its amazing dynamics with the ginormous red hurricane. The red spot was discovered about 100 years later after Galileo. It took a little bit better telescopes. The spot, by the way, is disappearing. You're fine, your children also. But, over the lifetime of your grandchildren or so, that really is becoming smaller. That reminds you that things are changing all the time. So the fact that things change here should not be a surprise. The universe is changing also all the time. What's interesting, though, is that many of these other bodies are much more interesting, much more exciting than we ever thought. A very diverse world, which is basically defined by volcanic activity, Io, all the way to icy worlds like Europa. And so if you look at this overall system and focus on Europe, you basically find a surface that looks really cracked and has a multitude of features that, frankly, by itself is really interesting. It has these cracks that change, distinguishedly so. So if we fly by Europe at a given place, the cracks are different. You're not surprised by that because you've observed ice elsewhere. So ice, including there, is in motion. And there's some other things that, of course, also shape Europe, and that is, I know there's cases also in the polar regions of impacts from celestial bodies, craters that are directly impacting the surface of Europa, of course, in part because Jupiter is so heavy. And it shields us here. There's a lot fewer of those impacts because Jupiter is hanging out in the solar system. But there's more on Europe as a result of it. So you have all those things. The most important insight, though, came from a mission in the late 90s by Marty Kivelson, who was the head of the magnetometer. So like you wouldn't exactly think of the magnetometer as a fundamental instrument for ice research or research kind of that body. It was mostly there because of Jupiter's strong magnetic field, which of course gives rise to radiation belts. But basically what she found is that as Galileo flew by Europa, that the magnetic field that is Jupiter's magnetic field and supposed to be steady, because the magnetic field is like, if you walk from here to Bern with a compass, it's not exactly changing much, the magnetic field. So if you fly by Europa, it's not changing much on a time scale of that. But what she found is a modulation of the magnetic field, which she basically interpreted correctly as a impact of a dielectric below the surface of Europa, namely water. You could do the models and convince yourself that basically deflection of the magnetic field is very much consistent with this body not being some kind of rocky, inert thing with some ice on top, but being an ocean world that is very much full of water. It has rocks at the inside, but an ocean world which makes us think about Europa in a very different way. It makes us think of Europa as one that has at the top, of course, a surface ice crust, has a thick ice shell, and then subsurface ocean and a rocky seafloor. And that the models that we currently have various parameters of these because we just don't know, for example, how thick the ice is. Also, its consistency, are there cracks in it? Like we've observed elsewhere, I'm going to talk to you about. But of course, what you'd like to have is what you do is you look at this and you look at this from the point of view of some of the models that have shaped our thinking. By the way, there's multiple models which says we don't understand it. Remember the difference between the reason you know how science works is kind of in times of ignorance, there's many models. That's the way it should work, models that make predictions. So it's really exciting to look at a model that looks at kind of the sub-ocean surface as a place where life can arise. For that, you need, of course, water. Water is a useful way of binding oxygen, which is otherwise a bad chemical. If you're in a career of building long chemicals that hopefully have a chance of life, oxygen is your enemy. So you better tie it up. And water is good for that because it's then there. But the other reason is also liquid water moves around chemicals and kind of creates a dating pool of chemicals, which is what you want as to build larger chemicals. So you need the energy, of course, to actually do these kind of chemical connections. And the stability over many years and billions of years, we believe, to actually have the chance, because the likelihood of creating life, which, by the way, we're having a hard time estimating, but the likelihood of creating life certainly goes up with time. And so kind of longer is better as we look at this. All these, we think, based on the understanding we have, is there. And so it kind of in that way, it looks a little bit like these kind of environments, which of course are always a surprise to me. Kind of the magnificent distribution of life everywhere on Earth still is puzzling to me. Kind of wherever you go on Earth, you go there. I remember once sitting on a plane next to some guy I didn't know, and we started talking about this. All of a sudden, he pulled out of his bag plots of life that he pulled from permafrost in Siberia. Turned out to be Jim Tichy. He was famous for that. But it's important that you sit next to the right people on planes. So you learn good things. So for me, like these kind of extremophiles are just absolutely stunning, both in these environments, also in the cold regions on Earth. And so basically what the Europa Clipper mission is, which is a mission that I actually was kind of in the going, but I spent a lot of time on making happen because of that idea. Is to really understand that ecosystem, both from ice, the ocean, the composition, the geology, the activities, and also kind of observing things that we have not seen, all on one single platform. This is the best we can do today. It's not a mission about finding life, it's about assessing habitability. And so the mission is a mission that has left this planet, and I want you to be part of this. It's here, it's always good in the morning to make a little bit of noise and fire, so here we go.
Live at NASA's Kennedy Space Center for NASA's Europa Clipper mission, a nearly 2 billion mile, 5.5-year journey to Jupiter's icy ocean moon.
And liftoff. Liftoff, and Falcon Heavy with Europa Clipper, unveiling the mysteries of an enormous ocean beneath the icy crust of Jupiter's moon, Europa.
Booster separation confirmed.
Bearing is separated, and those will be recovered by SpaceX's own recovery ship, Go Cosmos.
This is a big moment for the program, for NASA, APL, and JPL. Let's watch.
Europa Clipper separation confirmed.
And there you go. NASA's Europa Clipper probe, embarking on a long-awaited mission to study Jupiter's icy moon Europa. And what a sight.
Now they wait for acquisition of signal.
Quiet, I can attest to you. The other thing I also want to mention, there's a European mission that is going to a neighboring moon and doing a very exciting work, including with instruments that were built in Switzerland, especially at the University of Bern, where some of the best mass specs in the world have been built. Instruments that, of course, have Swiss technology and ingenuity, but amazing science capability in them, like so many of the instruments that are around. So if you go to Jupiter, it's this kind of a theme about going to the polar regions, or kind of these kind of worlds is hard. What makes it hard is something that Frank Drake, the father of exobiology of SETI, kind of figured out looking through a telescope in 1959. He figured out that there's a lot of radio radiation from Jupiter where there shouldn't be. And he interpreted it correctly as radiation that comes from particles around strong magnetic fields. And it's those very particles that are deadly to deal with if you go near Europa. So basically what you have to do if you go near Europa, you can't just sit there, because if you sit there after only 30 to 90 days, you're cooked. I mean, you literally have too much radiation, your electronics start failing because the radiation is so intense. So what you need to do is fly in, take data, recover, send out all the data, and then fly back in and pedal around. It's on its way. Will arrive kind of in 2030 out there. And of course, the biggest question that I have is like, okay, so we're looking for habitability, but the biggest question I have, are there plumes at Europa? We don't know. This is the best image of emissions of hydrogen and oxygen, which of course will be there if there's plumes. And basically, you could argue about this forever. Is there plumes? If there is another paper by the Hubble Space Telescope that said there's a larger likelihood, so either it's intermittent or not. And I want to tell you the principle that I believe we should use. If we have a chance of finding something important, we should go look. And so this is the instrument. It's a mass spec, similar to the ones that are done in Bern. Actually, the Bern people are very much, the Bern scientists from Bern are very much partners of this. It's an advanced mass spec that will go there and find really long chemicals if they're there. It may find absolutely nothing. And I remember pushing it on to the payload, because I always told everybody, if there's plumes, this is what makes everybody famous, not the other stuff we're expecting. So when in doubt, go look. When in doubt, go look. And so basically, I'm excited for that. Now, Enceladus, which is another moon nobody could pronounce until we found water. And not only water, but chemicals that came out. That's the other giant planet, which is of course Saturn. Enceladus has massive plumes leaking out. So kind of really filling. This is water vapor that is filling the environment next to Enceladus, which is only in 1 pixel of that. And it's filling the whole thing with not only water, but with alcohols and many other ingredients, which is a surprise to everybody. And so for me, the question, and now I'm bringing it to the Earth, right? Kind of what is keeping us thinking and awake at night is the question whether how we could in fact find in these environments life. And the problem is that the instruments that you need to build are not instruments that are easily checked in Bern or in Zurich or somewhere here. They need to go hang out in ice. They need to go hang out in an environment which is really unfriendly to many of these instruments. They don't want to be in that kind of temperature range. Those are two of the scientists that have been working together at various organizations, two of many. There's also scientists and companies that are basically already now working with the European Space Agency on an Enceladus mission to go after that object, which we have done with Cassini, have done whatever we did. We never built the mass spectrometer to actually see this stuff because we didn't expect it. So we just know that we filled the whole range of the mass spec with chemicals, like the whole mass range. So there's a lot of complex chemicals in Enceladus. So what they're saying is like, let's actually develop an instrument that really advances that thinking of the chemical environment of that. Also build the instruments for that. And for that, what you need to do, because of the fact that the environment, especially if it's a landed mission, is such in a different state, right? You need to actually create a sample acquisition system, the likes of which we've never built in space. We've never done it. And so learning how to do that and integrate it is one of these things that, of course, we're doing here in Switzerland, sometimes with collaborators elsewhere. And really, what we're really trying to figure out is how do we use kind of the analogs, the environments that you're in for other reasons, for the reasons that you all are working on. How do we use this, also microfluidics? We could be talking about multiple experiments. How do we kind of create an environment where we can, in fact, develop these instruments that want to go somewhere else in the world, but test them right here, whether it is in glacial environments or even in polar environments. That's a discussion we'd really like to have, and you should tell me whom you want to talk about, but in that workshop, I didn't attend last night because I did something else. Yesterday, I did something else. This is something, I hope it came up, but we'd really like to put on the table as one of those things that is there. An elephant in the room, let's talk quickly about it. The science support in the US is anything but stable right now. And kind of work that relates to the polar regions of the world is the most unstable of any of the work. I would just argue with you. It is the most unstable because it was already broken before Trump came in. And then, the uncertainties that came from the budgetary process and from other processes go on top of that. And so I would just really argue, sometimes we should look at what we do, not just from the point of view is where we can be leaders, but also from the point of view is how can we help the world. And I would just really argue sometimes these kind of investments that we make is not just good for us, but it's good for everybody. And I would argue this is one of those things we should really consider because important research, not just this, there's many other things that I have not had the time to talk about, is just stopping because of the fact that polar areas, polar regions are largely inaccessible to many of the federally funded research program in the US, but many other countries just really do not have the ability and the infrastructure to do that. So for me, that is the point I wanted to make here. Before I, of course, turn to my favorite celestial body, which is this one, our home that we have looked at from space. Kind of inadvertently, I actually believe the most important thing that happened by leaving the Earth on rockets like the ones I shared is that it enabled the view of our beautiful planet from the best staging ground to actually understand the planet. Our planet, whether we like it or not, some people don't, some others do, is connected deeply and globally. And many of the processes and systems that we observe are only understandable if you look at it from the staging ground of climate observatories, which is space. And the way we do that is many different ways. Technologies that have been developed over time, which are frankly stunning. There are images, of course. What's exciting about images, you all know the Sentinels imagery, the Landsat imagery. What is happening is that we're moving from images of 8 colors or so to images of hundreds and thousands of colors. That, by the way, is enabled by technologies that are now fitting onto satellites. I just visited a company that's just in the next few months is starting a manufacturing facility in Germany, where they build a hyperspectral imager that is described like I just did for $10 million. So that's what, by the way, the cheapest one I funded at NASA that did something like that was $150. What that tells you is that because of new technologies, by the way, it already is flying and it's working. So it's not like a dream. It's like what they need to do is scale. So what is happening is that imagery in the next 5 years will not only duplicate, it will 10x, 100x for the availability for research of the type that you're interested in if you're looking at imagery from space. This is one of multiple investigations. Think of gravity measurements. Gravity measurements are currently done by the GRACE mission series. It's a mission series that with Germany, the US, France has some contributions, the UK has some contributions. And it's basically 2 spacecraft that fly in lockstep around the Earth. And basically what you do is you measure the distance between these spacecraft to an accuracy that is comparable with atomic dimensions. So it's really accurately, and of course, if this is a mountain and I fly, the first spacecraft sees the gravity faster than the one behind it, and so like a harmonica at the Schwingfest, that distance goes in and out of these, and with enough models, you can deconvolve them. I'm excited about this technology, but what I'm more excited about is I've figured out, and you can all figure out, that the clocks we have available today, the best clocks that we can put on spacecraft, are only 10 factor of 10 off. If we're 10 times better than what we are, and by the way, we're in the land of clocks, by the way, in case you forgot that in watches. If we're a factor of 10 better than what we are, we can measure the gravity with this or better resolution on a single spacecraft because of one of our good people we also claim for Switzerland, Albert Einstein, who talked about general relativity, basically gravity measurement, gravity affecting time in a direct fashion. So we're a factor of 10 off from that. My point is, I gave you 2 examples. I could kept going. Space data in the next years will massively go up from where we are today already. And space data will be available and kind of support the kind of research and the applications that we have. This is the European fleet. I talked to you about a private company that I actually has made their data public. It's a company together with many others that are contributing to this. This is the European system. By the way, the Copernicus system is the best climate observatory in the world. It just is. There's nobody that is even close to it. In the US, frankly, what I did is like, as the head of science, I basically sat together with Joseph Aschbacher, who was the head of Earth Science, and basically said, look, why don't you lead and we put instruments on it? Because I can't sell in the US things to do for many decades. Like, you're better at that. Your people live in houses that are hundreds of years old, right? The US doesn't. And so kind of these longevity investments, Europe is the right place to do them and serves the world. And so in the US, we put a lot of instruments on these things, also built some of the kind of advanced technologies. But I just want to say these data are available and in most cases public, not even showing you the Earth's kind of the fleet of the US, again, with the asterisks that many discussions are happening as we speak. The point I'm trying to say is that basically 150 petabytes or so of data are available as we speak today, with a flow with some of the new missions of single-digit petabytes per year that are coming in, even double-digit petabytes. Because see, AI is not only useful on Earth when the data are down, but actually to choose the data that are actually sent down on a spacecraft, which allows you to build the spacecraft really differently. You can actually build a huge data container and measure everything you can and then decide on the ground what you want to bring down or automatically there. For example, if you're looking for fire or landslides or movement, you can focus your eyes there in a way that a traditional spacecraft cannot. So basically, the other useful aspect of Earth science and technology as in the AI space is the compression of data, which makes the data a lot more better to handle with compressions of 10x and only science loss of like 5% in many of the publications that have been done, some of them right here. So for me, the data magnitudes are quite stunning. By the way, that peak in 25 is going to go much bigger because of other people downloading. But the point is that data are being used. And by the way, a lot of this downloading of data, I just have access to this. I don't have the European data, but a lot of this downloading is not just it's not just academic organization. Actually, the majority is companies. So you know, people who want to make profit in the future understand that they need to get a better understanding of the environment around them because it affects what they're doing. And so basically a lot of the, many of the climate people now work for companies because that's where they are and that's what they use the data. So of course, you know, many of these data sets, I see experts in the room who can have built their career in part on kind of both measuring and understanding these data, both in a global and in a local fashion. And of course, this is the ocean, you know, the heights of oceans, the sea level. And what's important is that the measurements we have, both by gravity, but also by radar and LiDAR type of measurements, we can actually separate impacts of reasons why water rises. Why does the ocean go up? Is it because the ocean gets warmer? And because things get warmer, they expand, or is it because there's more water? And the answer is both. As you can see on this, we can independently measure all of these three curves. How much water is there? How much expansion is there? By measuring accurately temperatures and how much total water is there. And we can basically measure all three of them. And that gives us confidence. I'm confident in these. I get asked many times about climate change. I basically said, I'm confident in this because I think many of the models are really good, but I'm confident because we can measure it. Like we measure it. I go to the doctor and measure my blood pressure. I want to do the same with our amazing planet, right? So for me, it's measurements that I built my confidence on. Of course, the work that has happened observing from space, you know, bodies in the polar regions is just amazing. I personally, I spent a lot of effort on this kind of at NASA, and I think rightly so, also in the European Space Agency, the Crystal series and others are continuing these series and looking forward at this. What's so surprising to me is actually, I consider this one of the real puzzles. Kind of many of the model predictions actually really had to be revised over time. The melting of the Antarctic, which is not what I'm showing, is actually much faster than any model we had, unfortunately. And so basically what that tells you is the data are really critical and need to be continued. And we need to, of course, be in situ to kind of understand what the processes and systems are that are spending time on it. Now, I have never been to the Antarctic, so I only gave this talk because I asked you, will you bring me with you, and then you said yes. I was like, well, I'll give the talk. But by the way, the new guy that just started this week, you may have seen it in the news, the new system engineer we hired from NASA, one of the lead system engineers. I told him I'm giving a talk here. It's like, he said, I want to come with. So many of us have dreams, and all the books I read, right, of Shackleton. I once taught a whole class on Shackleton about leadership and crisis. I love that these books. I read them as a kid. So I did not go there. What I did is I sat on a helicopter, which is a lot easier. And I flew around kind of icy worlds that are closer to us, including this one, of course, which is, this is a good week ago or so, 2 weeks ago now, which of course, to the untrained eye, looks like a bunch of debris. To you, you immediately know there's over 50% ice in this thing, and the dynamics of this system is very different than it would be if it was just rocks, because the entire kind of how it sticks to each other and how it actually slides into the valley is very much different depending on what the physical structure is, the integrity of this. And of course, if you look at this, I was trying to say, Dr. Meyer was with us. This was in preparation of GeoLab, which is what I'm, of course, talking about now. We looked at both the warning systems that are there, but also the systems, how they, in fact, affected the community that is there. I just want to say how deeply appreciative I am of the people who supported the decision-making, which saved so many lives. Some of these people are right here, so thanks to you if you're part of this. This is the way, I believe, also we as scientists need to speak and show what we're actually doing for the world. We should learn from this. Many of the puzzles are still there, scientific puzzles about the final phase of this event, for example, where the rock slide goes on top of the ice. Why is the disintegration so fast? I've been talking to scientists. Perhaps one of you knows the answer. So I heard many answers, not one, which tells me there's much to be thinking about. Of course, the water is still there. This is as of a good week ago. And the reason, of course, is that gravel that you looked at is 50% ice, and the ice is melting. So there's source of that. The other thing that you should know, in that mountain, you stand in front of that mountain or sit in a helicopter in front of that mountain, the hill is still in motion. Like it's still falling on a regular basis. Debris is falling out of that hill. And so for me, whether you look at that or you look at melting events like this one, which I always thought is one of the most beautiful sights in all of Switzerland, this magnificent glacier, it just absolutely takes my breath away still. That's why I ski and hike and bike and, like in these kind of environments, because first of all, you're closer to the sky, but also because it gives you a magnificent view of just the power of nature, but also the fragility of nature that I, of course, I'm demonstrating with this, and events that affect communities like this. I just want to tell you something. So I'm glad for Dr. Mayra and his people who are keeping communities like Zermatt safe. But let me just say, if everybody knew what's up on top of them in detail, they would be more interested looking into the mountains than they are. So there's enormous work that is happening to protect these communities and work that we can support. And so for me, whether it's break-offs of ice, things that are in motion are measured by radars, by cameras, and also by gravity, by a variety of sensors. Kind of what I learned from this is that in the Alps, and that, of course, there's hundreds of hotspots that are monitored with various amounts of sensors. But what has happened in the last decades is that so many of the events actually happen in areas where nobody was looking. So kind of there are surprises that are happening on a regular basis. By the way, not just in the Alps. Himalayas are really, many of you work there, are really critical for that, where, of course, if you look at the 1,000 to 2,000 people that die in landslides and mudslides per year, in the world. Many of them are in these regions where in the back country something happens and no warning propagates fast enough for that. And so basically the question we need, of course, is surveys that detect movement and patterns and advanced cost-effective drone landscape sensors that can enable that. That's not my words, that's the words that are theirs. Of course, there's some of these things exist. Our goal is not to duplicate what exists. Our goal is to help advance from there towards the resolution, both in time and space that exists. Interestingly enough, as you know, the European satellites that I talked about are all in polar orbits. The Alps are not polar, south-north. We would have a lot more data if they were, but they're not. So the good news is we're measuring everything on globally, which is why they are polar. The bad news is we're not measuring enough on the Alps. And so for us, like who are spacecraft designers, like, I wonder whether there's designs where we could really help these kind of things. And again, we're not talking hundreds or of millions and billions. The question is, how do we get some of these spacecraft that are built already to actually do this? So it's because of this and multiple very practical ideas that a number of faculty have come together, initially focused on ETH, to really create a lab that is very much unapologetically focused on that small view of the global Earth data. A small view that, of course, transforms the abundant space data into practical solutions that create economic value where that is possible. I want to just talk to you about an application there and address some of the most pressing challenges. We think, as I told you at the beginning, we're in a unique position for everything we already said. I want to quickly talk about economic values. We know that half to three-quarters in many cases of fertilizer that's put out in the fields is absolutely not needed. So it does not do anything other than going into the lake down the valley. And so basically economic value for a farmer, I grew up in a farm environment. I know they're not rich people. Let's help them save money by giving them information to actually tell them where their fertilizer is helpful and where it isn't. Because if I can create them savings for them and a better environment, that's good. Because it amplifies without any necessary regulatory force, which, as we know, is unstable. We're seeing that in the US right now. Frankly, many of the European discussions, we're seeing it also. A lot of things that people thought are checked off are being unwound again for many reasons that I'm sure are understandable. So we really want this to be a global standard for space data applications and bridging the gap between abundant satellite information and world problems. We're great if people do science paper. What we do not set as a key metric is the number of science papers, fundamental science paper as output. We're really in the application phase, want to be more downstream in partnerships with the application communities and really focus on actionable insight. We think there's amazing science in there that is absolutely publishable. It's also aligned with many of our students' thinkings because they want to help the world in a direct fashion. And we think we have enormous advantages, all of which I've already talked about. So there's a number of applications that we've thought of. With the 100 million, there's some cost sharing from ETH. There's additional money for real estate. We've already raised some other money for data systems. With that, we can't focus on all applications. But what we want to focus on are applications where we have the most to offer in the context of actual utility. And so that will require work. And so we think landslides is one of them. We also talked to some of the government entities already. They're really enthusiastic about this. But what are the others? We don't know. I'll show you in just a minute how we're doing it. But first, let's talk about when. Our full expectation is to start now. You saw ETH Zurich Spaces mentioned as a kind of a launching organization for that. The reason for that is we're passionate to get started. You know how fast or how slow it is to hire people. The director is starting in less than 2 weeks. and we made the offer 3 weeks ago, or less. So we're getting started, and we're going to support them with our own staff, so we're not going to have to hire. We want to be really cheap because we want to put the money into the research and be absolutely cheap in how we do that, kind of knauserig, I would say. So basically, of course, we want to hire the people we need to support, but mostly we want to hire the researchers and application experts. We want to scale integrate. Part of this, or the hub will be in Luzern, Canton Luzern. We're going to start right away, but then figure out where and how to move. Because as you know, the only way you can scale is the government entities and the startups, the companies need to be part of this. And so we're planning, we're talking to a number of them already. This is the group that kind of at the beginning helped put this together. I'm sure you've already met Frena Gries, otherwise please meet her. It's just been absolutely fun to work with her. Just absolutely impressive. She is very much focused on forestry and, stabilizing kind of some of these mountains with forest, but the forest health by themselves. There's many others, including also these mobile platforms, Roland Sigrid and others are focused on. So that's what we're focused on. The way we're going to do this is we start at ETH. That's, of course, that's what we did, but we're going to be wide open. We want the best ideas, and we right now with you and others, we're going to start the discussion of how we actually kind of make the circle bigger. From the beginning, as we talked to the founders here, we always said we want to do this in partnership. So again, our goal is not to compete against the people who are already there. It's to compete with time about the urgent applications and urgent threats that are coming to us by the changes that are affecting the entire planet, including the regions that you study. So thanks again for everything you do, and I look forward to the discussion.